Okay, let's begin.
So we had an example to finish up last time, so let's just get that out of the way. Find f prime by the definition. Which you had to do on the quiz day. And it was the last example, I don't remember what it was. Part B, maybe, was the square root of x. And you had to find f prime. So, what is the definition of f prime? How do you define that? I think that was on my side. Yeah, Laura?
The limit as h approaches 0 of f of x plus h minus f of x over h.
Right. And applying that here, what is f of x plus h?
Radical x plus h minus radical x over h.
How do you find that limit?
You could take the conjugate.
What's the conjugate?
Radical x plus h plus radical x.
Right. Want to rationalize the numerator here? Multiply and divide by the conjugate. Notice that in the numerator, that looks like a minus b times a plus b. So that's the difference of squares formula. So that becomes a squared minus b squared. A squared minus b squared. Over, now you just multiply across. Now, just a little warning here. Students
Don't you not?
often do this. Huh? What?
Don't you not want a radical in the denominator?
No, it's not a rule. Never expand the denominator. So if you multiply this out, you're actually just going to have to refactor it later, so don't even bother. Moving on, what's going to happen is the x's are going to kill each other. And you have limit as h approaches 0 of h over h times. And the h's cancel. And what is that? Yeah?
1 over radical x. Square root of x.
No. It's a plus h here.
So 1 over 2 square root
1
of
over
x.
2 squared x. And in fact, we can write that as another rule. Remember this notation, hopefully from last week. You can say the derivative with respect to x of radical x is 1 over 2 radical x. So now that's something we know. That's actually, you can take that as a rule. The derivative of radical x is 1 over 2 radical x. And of course, remember what that means. It means 1 over 2 radical x is a form that will give us the slope at any point along radical x where it is defined. And so this is read as the derivative. Sometimes you might leave off the variable when it's understood. With respect to x, x is your independent variable, it's your input, it's the guy that you're manipulating to see what's wrong with how the function responds. Of the square root of x is, right? 1 over square root. That's how this is read. The derivative of radical x is blah. Okay? And that's a rule that we know now. So far we know we know what the derivative of x squared is, we know what the derivative of a constant times x is, we know what the derivative of a constant is, we know what a derivative of 1 over x looks like, we know what the derivative of the square root of x looks like. So we know how to use the definition to find the derivative of several important functions, and that's another rule that we have now. So the rest of the class, we're not really going to do any computational stuff. We're going to talk about some important ideas and concepts that you guys need to be aware of. jump into that. One thing you want to know is interpretations of the sign of a derivative. So when it comes to the slope of something, let's say slope n, and you have something that looks like this versus something that's horizontal versus something that's coming down like that versus something that's vertical. These are various situations using straight lines. How would you describe the slope here in terms of the sign? Yeah?
Positive.
Positive. So here, n is positive. Here,
0.
it's 0. Right? Non-negative. Here,
Negative.
here n is negative. Here,
Undefined.
and undefined. Now, of course, remember, derivative is a synonym for slope. It actually means exactly the same thing. So here, what we could have said was derivative is positive. Here I could say the derivative is 0. And here I can say the derivative is negative. And here I can say the derivative is undefined. Now, we'll talk about more situations where the derivative is undefined later, but in this case, it is. You have a vertical line, the derivative of that line is undefined, at least with respect to x. And the important idea is this can be applied in general, not just the straight lines. This can be applied in general. So for example, if you have a function that's not necessarily a straight line, but it has maybe this behavior, what you can realize is that if you were to sketch tangent lines at some points, the tangent line is always pointing up. Notice that it's pointing up with a positive slope, and whenever a function is having this sort of behavior, moving up as you go from left to right, we would call it increasing. Now here, I want you to notice that f here is increasing, we would call it. Here, f is decreasing, we will call it. And here, it's sometimes called non-decreasing or sometimes non-increasing, depends on the context. They're both the same thing. It's not moving up or down. So you can apply this to curved functions just by watching the tangent lines. Whenever your tangent lines are pointing like a straight line moving up, we say, oh, the function here, the derivative is positive in this region, and whenever a derivative is positive in a region, you can interpret that as increasing. Increasing means you're getting bigger over time, right? So as you move to the right, you're getting higher. Decreasing means you're getting smaller over time. As you move to the right, you're getting smaller, you're getting lower. So f is increasing in a region if your first derivative is positive there. This is important. F is decreasing if your derivative is negative. So this is an important concept, it's an important interpretation. We can talk about increasing and decreasing in terms of the derivative of a function. Whenever a function has positive derivative, the function is increasing, meaning it's moving up as you go from left to right. Slope is negative, it's decreasing. You're moving down as you go from left to right. That's a very important interpretation. And there are many consequences of that, and we'll explore them. Another very important concept that we want to know about is going to be the notion of higher derivatives. I don't really want to tell you about it at this point. Yes. There's also the notion of a higher derivative. The idea is sometimes, after taking a derivative, you may do so again and again. Right? Now, not all functions are this nice. There are functions out there that if you take a derivative one time, you won't be able to do it again, but we're not going to see functions like that in this class. Pretty much all the time, the guys that we're looking at, you would be able to take derivatives repeatedly, right? So for example, we did y equals x squared. We know that derivative of that was 2x. Look at 2x, it's another function. And based on the fact that what we derived last class, we know the derivative of that is 2. And 2 is a constant. We know the derivative of that is 0. And we can just keep going. We can keep taking derivatives again and again. So I can take a derivative of a function, take a derivative of the result, take a derivative of the result, and so on and so forth. These are called higher derivatives. And it basically means you're taking a derivative of a derivative of a derivative as many times as might be possible. And so the notation that you can use for this, well, there are two versions. Of course, there's the Newton notation and the Leibniz notation. And the derivative we're talking about. So, Newton notation, you might call the function f of x, while Leibniz might call it y. And this, the original function is the 0th derivative. You've taken no derivatives. There's 0 derivatives. Now, of course, the first derivative we know about, first derivative. This we call f prime in the Newton prime notation. Leibniz notation is going to call it dy dx. That's the first derivative. That's the slope of the tangent line to the function. Now, you can sometimes do more derivatives. So this might be a function that you can now take a derivative of. In the Newton notation, you add a prime. Right? So you write 2 primes, or f double prime of x. In the Leibniz notation, you get d squared y dx squared. So it's like you had y, you took d dx of this, kind of like we had in the notation over here. You get that. If you take d dx of that, the d is squared, the dx is squared, and you get that. This is the second derivative. Of course, you can keep going. You can go to the third derivative. And you can keep going. Now, eventually, as you can probably tell, if you take too many derivatives, this notation is going to get kind of annoying. You want to talk about the 17th derivative. You don't want to be drawing like 17 primes. So eventually what happens is, usually beyond 4 derivatives, people get lazy and write this down. You write a power, but you write the number in parentheses. And that would represent the nth derivative. Right? So, example, if I write f to the parentheses 17 of x, this is the 17th derivative. It means I took a derivative and I kept taking it 17 times over. Right? So, in the Leibniz version, dny dx to the n for nth derivative. So I could also do here d17 of y over dx to the 17th derivative. Now, for our class, these are the important derivatives. We're not going to really apply the rest of them, even though they do have applications that are very important. Applied Calc 1 only cares about these. The first, the 0th, the first, and the second derivative. These are the ones we care about. So, we know about the first derivative, at least what it is. We'll continue to learn more about it as time goes on, but let's talk about the second derivative for a little bit. This guy has many applications. We're not going to talk about all of them, but here are a few. One is to motion, right? As in what you would study in general physics. Right? So usually chapter 1 of a general physics course is going to start out talking about motion. This means when we're talking about if I have a function that measures the position of an object, right, at time t. You plug in the time, the output s tells you what is my location at that time. If you are to differentiate the position function, you obtain what's called a velocity function. This is the rate of change of your position, or it's kind of like speed in a particular direction. Now, it turns out that if you were to differentiate that again, in other words, find a second derivative, you obtain what's called the acceleration function. Now, the acceleration function is the rate of change of velocity, which means it is telling you if you're speeding up or you're slowing down. So this tells me, where am I? How fast am I moving? Am I speeding up or slowing down, right? So once you start to go to the second derivative, it starts to tell you how your speed is changing. One important constant here when it comes to acceleration is the acceleration due to gravity. Sometimes it's considered minus 9.81 meters per second squared, or minus 32 feet per second squared. And what that means is neglecting air resistance. You drop an object and it's falling to the earth is going to speed that object up at 9.81 meters per second squared, or 32 feet per second squared. So you're holding something, it's moving at 0 speed, you release it. After 1 second, it will be traveling at 32 feet per second. After another second, you'll be traveling at 64 feet per second, and so on. Every second that passes, it will add these numbers to its speed. Now there's something called terminal velocity. Eventually it'll speed up to a point where it won't speed up anymore, but until then, this is how much it's adding to the speed every second. This is the acceleration due to gravity. Very important concept. Now the third derivative, that also has a nice physics application. It's actually called a jerk. So if your friend calls you a third derivative, it's not a compliment, just so you know, just in case you have a friend who would call you a third derivative. So, but these three, very important. We're going to do lots of applications with them, but at least now I just want you to know that this is a thing. Position, velocity, acceleration, you can talk about motion in terms of physics, in terms of these quantities, and acceleration in particular is a second derivative. And it describes how your speed is changing over time. A second thing that's very useful is concavity, something called concavity. Now this is a geometric term, and it refers to shape. What kind of shape? What do I mean? I'll describe to you the shape that we're talking about. F is said to be concave up if it always lies concave up in a region. Yes. Doesn't have to be concave up everywhere. So here's a function that is actually concave up. Here's another function that is actually concave up. Notice that at any point, if you were to draw tangent lines to this function, the tangent lines will always be underneath the function. They'll be cradling the function, right? So it's called concave up whenever this property happens. Now, one thing you'll notice here with concave up, note that the slopes are increasing. Here your slope is positive, here it's more positive. Here it's even more positive. It getting larger over time. Similarly here it's negative, but here's less negative. Here's less negative, it's increasing towards zero. Over time, as you move from left to right, your slopes are actually getting bigger. This is a defining quality of a concave up behavior and results in this kind of shape, this kind of bend called concave up. And since your slopes are increasing and increasing means derivative is positive, this means the derivative of the slopes is positive. But what is the slope? Well, the slope is f prime. So it means that the derivative of f prime is positive. What is the derivative of f prime? Well, that's the second derivative, that's f double prime. i.e. f is concave up on a region if f double prime is positive there. So that's another important idea. And that's also an answer to one of the bonuses on the quiz where I said, using an inequality, describe what it means to be increasing. The answer was f prime was greater than zero. Using an inequality, describe what it means to be concave up or concave down, because depending on what but then you were supposed to write f double prime greater than zero. So that's concavity. And of course, if you have concave up, it would stand to reason that there is such a thing as concave down. There is. So similarly, f is concave down in a region if it is always below its tangent lines. What would such a function look like? Well, it would be like this, or that. Notice that at any point, I start to draw tangent lines, the function, the curve is going to be below the tangent line. And of course, you'll notice here, slopes are decreasing. And so immediately we can get, via the same kind of argument, I'm not going to write out everything, that f is concave down in a region if f double prime is negative there. So you can talk about concavity in terms of the sign of the second derivative. So that's a geometric interpretation of the second derivative. So for the first derivative, a geometric interpretation is increasing and decreasing. Moving up as you go from left to right means your derivative is positive. Moving down as you go from left to right means the derivative is negative. if you have this kind of bend, it means your second derivative is positive. If you have this kind of bend, it means your second derivative is negative. Now I want you to note, because this is often a point of confusion, this has nothing to do with increasing or decreasing, but rather shape. Okay. So, in terms of concave up versus concave down, you can be increasing or decreasing in either scenario. So, I can be concave up, here it's concave up and increasing. Or I can be concave up and decreasing. So increasing and decreasing, it's different from concavity. So here, in both of these situations, your f double prime is positive. However, in this situation, your f prime is positive while your f prime is negative, right? Versus you can have this guy here, or that guy there. So this is concave down and increasing. It's moving up as you go from left to right, but it's bending this way. Concave down and decreasing. So in both scenarios here, your second derivative is negative. However, over here, your first derivative is positive, while over here, your first derivative is negative. Right? So you can be increasing or decreasing in the whatever your concavity situation is. Concavity has nothing to do with increasing or decreasing. But another thing that you want to remember, there's a little mnemonic here. You want to remember who's who. We haven't seen this before. We call it concave up, like a cup. It's like you can hold water in something that's concave up. And we call it concave down, like a frown. So you can be up like a cup or down like a frown. Concave up like a cup, you're up, you're happy, you're smiling, you're feeling positive. Down like a frown, you're sad, feeling negative. In terms of second derivative. So concave up like a cup or down like a frown. So you're either shaped like a smiley face or a frowny face. And in terms of that shape idea, concavity is how we can determine it. And concavity is determined by the second derivative. Your first derivative tells you whether you're moving up or down. Your second derivative will tell you how are you shaped while you're moving up or down. It's another interpretation. We'll stop there, but we'll continue this discussion next time. Start off with some more important ideas